Thank you so much, Max. Good morning, everybody. We are super stoked to be here for day 2. I'm not going to make another introduction to who I am. I've seen you all a few times yesterday, but we have my dog just rolled in, so I guess he will maybe introduce himself. This is Mosh. Anyway, so for day 2, we have a really fun workshop for you guys. So yesterday we talked a little bit about King's distributed systems and distributed compute labs and what we're trying to do with this technology, but we didn't really give you much more than a sentence about the actual platform that we've built right here in downtown Kingston. So today I have the honor to welcome Dan, our CEO, and Connor, our head of BD, both Queen's alum, as well as Ellie, who is both a member of our AI task force and outreach coordinator, to show you guys first and to tell a little bit more about our platform, how it started. Dan will do my favorite demo of what was the problem that started this whole thing, and then we'll get to the fun part where you actually get to play with this a little bit, and hopefully this inspires you to maybe consider playing with it some more with your projects within QMine or in the future. So yeah, I'll pass on the mic to Dan and Connor, and then I'll just come in at the end for 1 minute to tell you if this is something that is fun for you, what will be the next steps. But with that, and one more thing that I wanted to say is please do ask questions throughout the talk on the chat. Ellie and I are going to be looking at all time, and if stopping Dan and Connor as needed. But we love questions, we love engagements, we love derailing our plan based on what's of interest to you. So if there's anything that is unclear or anything that you were like, I really want to know, something weird about the back end of how you designed this, please ask. We'd love to answer. So thank you so much. And Dan, mic passed on to you.
All right, thank you so much. First of all, let me show my bias. QMind is by far, I think, my favorite event, favorite group of students of all the maybe I shouldn't say this out loud, but of all the events we do, QMind is, I think, one of the ones we go back and support the longest since we were a startup, and we're still a startup. And we've always been so impressed by the quality and innovation and thinking and people coming out of that group that we've recruited many of them as part of our group here in Kingston. So you heard about King's distributed systems and distributed compute labs, and we ourselves have been struggling with that story, sorting it out for a little while. King's is the company that's building the technology and hiring everyone and deploying everything. Distributed Compute Labs is the educational nonprofit that engages with student groups and universities around the world and provides the technology DCP for free. The demo that Topaz asked me to deliver, DCP.mn, that's the classic, it's the nostalgic. I've been showing that for like 3 years now. It was the first prototype that this company built just to show what it is we were doing. And so we segregated it and shoved it in a container, and it still works 3 years later, which is pretty cool in one sense. I mean, it's not cool because people are probably tired of seeing it by now. You probably know exactly what I'm going to show you, but it's cool because it never broke. Forward and backward compatible, and that's one of the strengths of building on the web stack. So before I jump into that stuff, I also want to talk about some of the questions in your Kahoots. That was awesome. So Donald, 3 cheers to you for hosting that game. It can seem nutty and bonkers, but it was actually excellent. You made a stat about venture capital going, increasing by 3 to 5 X in the AI solution space. You're right. And all of these companies that are building these AI solutions are deploying them in Azure or AWS or GCP or somewhere else. They're spending between 15 and 55% of their revenue on AWS, Azure, and GCP. So imagine all of you are building really cool tech, but you're going to turn around at some point, and you're going to operationalize it, and you're going to try and commercialize it and make some money, build a company, and you're probably going to park it in the cloud somewhere. You're going to turn around, you're going to get money from your customers, and you're going to turn around, you're going to give half of it to Amazon. It's not a pleasant feeling. We don't know because we don't do that, but we're trying to come up with an alternative to that. So DCP is, it sounds like TCP IP, it's built on the web stack. DCP takes computational workload and spreads it around the computers that are around you right now, right here today. We'll do that demo shortly, but one of the academic visions is, hey, those 5,000 computers on Queen's campus doing nothing right now, or other university campuses? What if we just turn them into a cluster? And this doesn't use Docker container Kubernetes. It doesn't use VMs. It's completely radically different. And what if I said it was free? So that's DCP through Distributed Compute Labs. So I'll share my screen. I'll show you the good old-fashioned demo, and then we'll talk about how much hacking we've done over the last year and up the ante, because now we're doing some hyperparameter optimization with DCP, and we're actually starting to be part of the big leagues. Almost good enough that a group like this might try attempting to bang on it and see what works, what doesn't, what we can improve, and what needs to come into this, so that next year when we present and sponsor QMind again, we want to show more step function improvements. So without further ado, here's the good old-fashioned demo. Oh, and wait, as a segue from the Kahoot question, we talked about 3.5x in the venture investing in AI-based companies. But you know what doesn't, what scales with that is the amount of compute required. So between 2012 and 2018, so this stat is almost 4 years old, there was a 300,000 times increase in the amount of computing power required to power AI applications. So venture investing tripled. The amount of computing power required to back all of that was 300,000 times increase. Now that's nuts. So that's a doubling of compute power required to support AI every 3.5 months. And this, ladies and gentlemen, is why Amazon AWS, Google Cloud, and Microsoft Azure are eating the world. Software is eating the world, and cloud is eating software. And it's only increasing with the cooler and bigger things we do. Well, the more compute it takes, and so no longer are we building bricks and manufacturing windows and like the bread and butter stuff. Now we're manufacturing data centers. There was another Kahoot question. Sorry, I'm rambling here, but it's just important to put all that knowledge in the Kahoots into an awesome context. We talked about how 90% of the world's data was created in the last 2 years. You've seen nothing of what's to come. The Square Kilometer Array, which is a new gigantic space telescope, synthetic aperture radio telescope array, will produce, I believe, 13 petabytes per second when it becomes fully operational in the next 5 years. That, I think, is equal to some stupid amount of what the internet already is right now per second. So data is definitely the new oil, and everyone who's at least half decent at processing that data to turn it into actionable insights, and by that I mean computer scientists and data scientists, will have open green field to make money and companies and or rewarding careers and what have you. But equal opportunity will be ethicists and policy makers who are going to be involved in the governance of data and compute. So you don't have to be purely, in fact, you shouldn't be purely a technocrat or a technical person. You absolutely need to balance that with ethical, moral practices, because we will rip ourselves to pieces if, as a human species, if we're not careful with this. Okay, on that happy, somber note, I'll just do the old-fashioned demo, and then I'll hand it over to Connor and Ellie to tell you about the actual cool stuff under the hood here. This is just a web page, which means I can share it with anyone as easily as a Google Doc. Well, that's kind of cool. So if I want people to do compute, I don't have to send them all my MATLAB files and a container containing data or any of that crap. I just send them a link, and then they can automatically open and read all the cool stuff that I've been researching and dig into the math and correct me where I'm wrong, which is great. But in this paper, this web page, I'm talking about an electromagnetic coil pulsing a sinusoidal magnetic field onto this bilayer conducting and ferromagnetic tube, which means it's made of ferritic steel, maybe an aluminum layer or something like that. And the different magnetic permeability and conductivity of both these layers will create an interaction of magnetization and eddy current induction simultaneously, interacting at all of the boundaries and creating their own magnetic fields that will then go and induce countercurrents within the coil, the driving coil in the first place. And the interaction of those fields will obviously lead to some very interesting complex mathematics. But once we go through the pain of solving those equations, so solving the induced current densities, we can take the cross product, the magnetic flux density, And that gives us the force density. And if we integrate that force density over the volume of the coil, we'll get the total force. And that's what these two equations here are on the right. So we have the axial force, so the electromagnetic drag, and the radial force, which is the radial force with that levitation of that ring or that coil around that tube. The problem is we have to do a lot of numerical integration, and the kernels here are rapidly oscillating, so we need adaptive quadrature to actually perform those numerical integrals, and that takes a lot of compute power. So it would take my laptop afternoons to run these computations, much like some of you developing some cool AI hyperparameter searches and other stuff would require sometimes minutes, sometimes hours, maybe even days if you're doing gigantic data set searches and refinements and so on and so forth. So unlike normal scientific papers, this one's interactive. So I can just punch in some numbers, and I'm going to plot from 0 to 100 meters per second. That coil moving along the tube, we'll do by steps of 1. All the rest of this is modifiable, doesn't matter, who cares? And I'm going to say compute. Okay, great. So now nothing's happening because I got my progress bar, but I have no compute nodes. Right now I need compute power, and therefore I will just open a tab and do DCP.mn and hit start. And all of a sudden, my laptop is now part of this compute network. And you can see the progress bar is slowly moving. If everyone else in this audience does DCP.mn and hits start, this will go faster and I will stop talking sooner. So let's create a compute cluster altogether. DCP.mn. Punch that in a browser tab on any device you have around you. I don't care if you have a Mac or Windows machine or Linux or whatever, a fridge with a screen in it. Just type dcp.mn and hit start. And the more people join in, the more computers there are. The more computers are, you can see it's really going faster. Boom, 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 boom. The more slices of the job get sent out and then get computed in parallel. And since developing this simple demo that's still chugging along here 3 years later. Right now, you can see it sort of paused towards the end. It's stitching all the results together, and it's going to plot them pretty shortly. Since doing this, we've done nuclear fusion simulations. We've done some initial hyperparameter tuning. We've done some tutorials. We've done some, not magnetohydrodynamics, but some computational fluid dynamics and all kinds of stuff. So the idea is if you had 10,000 computers at your university, and you could hook them all together to make essentially an ad hoc Beowulf cluster to distribute your calculations as easy as clicking on a link, what would you do? And anyway, the API behind this is actually like 5 lines long, but I do know that Connor is going to show that, so I'm going to let him show you how we actually did that and not steal thunder. So thank you very much for watching me give that demo, hopefully one last time, as we'll evolve to something cooler. But for those who've already seen it, a little shot of nostalgia, that's us building DCP right here in Kingston and actively engaging students to help us make it better and bring compute networks to their universities and hopefully make this technology free and accessible so that we can democratize compute so that it's not a game for the rich and everyone around the world can do it. Thank you very much. Connor, I think it's over to you, or is it Ellie?
Thank you very much, Dan. Hi everyone. What I'm going to talk to you about today is a little bit less theoretical physics and a little bit more about those 5 lines that Dan mentioned, because the beauty of the distributed compute protocol, DCP, is that it's application agnostic. The same 5 lines of DCP code will run very simple applications. The same 5 lines of DCP code will run theoretical physics applications. So I'm going to show one of those very simple applications so that hopefully you can take out some of my application-specific code and use the DCP-specific code, plug in your own application, and start distributing some of your compute loads. So this will be involved. So if you would like to be distributing workloads over DCP, please feel free to follow along. I'm going to be giving some instructions, and if you follow them, by the end, you'll be distributing work on our network. So without any further ado, I'm going to screen share here. Okay, so first, just a little bit about the workshop that we're going to be doing. 4 steps with a step 0, so kind of 5 steps. But here is the first step. We're going to come back to this one at the end, but we're going to need to set up some workers for us to deploy all of our compute work to. And we're going to need to configure those workers to make sure that you're not spending all of my compute credits, that they'll all kind of flow in one nice circle. But for DCP applications, you need 4 simple things. The first is an input set. This is data that is going to go distributed to a bunch of different workers. Those workers are going to do some work on them, and then they'll come back and be collated. So your input set is the data that's going to actually be distributed. So the application that I'm going to show you is going to be very simple. We're going to take a string, so just the string yelling, and we're going to split it up into characters. And that will be our input set, is this array of characters. And then what we're going to do is we're going to turn that string 1 letter each into uppercase, but each worker on the network is going to handle 1 letter of the string, put it into uppercase, and send all of those results back to us, and we'll have an uppercase string at the end of it. Obviously not very computationally complex, but like I said, it's to just show that the DCP code stays the same even when the application specific code does not. So that's our input set, and those are going to be our slices, each character of the string. Next, we need a work function. This is what each worker is going to actually do to an element of the data set. So this work function is basically, hopefully, the longest step of your application or your program, and hopefully a very parallelizable step of your program. So in our case here, the work function is going to take 1 letter. It's going to return it in uppercase. Very simple, but same format for uppercase for theoretical physics. That progress call in the middle there, that's just a little bit of DCP specific code that just lets the worker know that the slice is active and still running. You don't have to worry too much about that for very short slices, but when you do run longer DCP jobs, progress needs to be called more frequently, just to let the worker know that your progress on the job hasn't stalled and needs to be cleaned up. Shouldn't be an issue for this job though. Our next step is compute.for. So let job equal compute.for input set work function. Pretty simple, pretty cool. It's very clean. I love the way that one sits. But essentially, that takes each element in the input set and maps it to the work function. Sends that work function in 1 element of the input set out to a bunch of workers. Waits for them to do their work. There's one optional line here that we're going to add to our programs, which is job.compute groups. So this is not necessary to include compute group information. But what is a compute group? On DCP, if we just send a job out, it could go to anyone's computer that's working on DCP, any DCP worker anywhere in the world or space, if the ISS happened to have some computers that turned on DCP.work. But what compute groups allows us to do is to choose a subset of those workers on the entire network. So why is this relevant? Well, it means that we can concentrate compute power into a certain area. But there's also applications for this where certain companies, hospitals, banks, government corporations may want to do computing without any data leaving a building, without leaving a premises. And so you can set all of your computers idly in a building to be working in one compute group and send work only to that compute group, get work only in that building, have it be super secure, but also unlock the power of your idle computing. It's really cool. So we are going to use a compute group today so that we each are going to set up some workers, set it to this compute group that we're going to spin up here. It's not going to be key and secret. Those are placeholders. And then we're going to send work to each other all within the group. So the work that you send out is only going to go to fellow QMind members. And finally, we await our results. Let result set equals await job.exec. This is just JavaScript telling us our asynchronous program to wait here for our results to come back. Once that's done, we're just going to handle our results. So your application will probably have different result handling because you may want to do something with your data when it comes back. But for us, we're just going to take the characters that are capital letters, put them back into one string, and print them out. Super simple, but really cool on the implications for distributed computing. So here's what it looks like a little bit more visually. We have an input set on our computer, yelling. It's our client, our computer. We run compute.for on that input set. We give it a work function. And the workers each pick up one slice, one element of our input set. We wait on our client, on our computer, while the workers run the work function, each on one element of the input set. When they're ready, when they're done, they'll send that result back to our client. And when our client gets all of the results back, we can process our results and do with them what we want. In this case, we're just going to print a nice capital string. So let's try that. I haven't been able to see the chat while I've been sharing here, so I'm just going to do a quick check-in. Okay, great. So we are going to take another look at step 0 for a moment. So the first thing that we're going to need to do is set up some workers. So we're going to go to dcp.work/hackathon. This is our entrance way to our little compute group for Camp QMind here today. The password is DCP 2021, and I'll put that in the chat in case people don't get that. But the URL is dcp.work/hackathon, and the password is lowercase DCP 2021. This is a worker. If I start this up, it's not going to start working on anything because there's no work in this compute group. It doesn't have any work in it. If I went to the public one on just dcp.work and I started it up, there probably are some jobs kicking around the public network right now that my worker could start working on. The next thing that we're going to need to do is we're going to need to get you some keystores. So what are keystores? They are essentially just bank accounts for compute credits. So when you're doing work with this, worker, you earn compute credits. And when you deploy work, you spend compute credits. And I'm just hearing that there's a question on the stage. How does the credit data banking system work? What is a credit? Great question. So if I log into my portal account, you don't need to do this for the purpose of this tutorial. So this is just a little sidebar here, but this is the DCP portal. It's going to look a little different in a short amount of time, but what we can do from here is manage our accounts. So this is a Keystore. What this is it's a cryptographic address that holds an amount of credits for me. And these compute credits are earned by doing work on dcp.work, as we will be doing shortly. And then I can download these keystores and use them to deploy jobs. And it will spend the credits that I have earned in this account. You can also deposit money into the account to get more credits, and you can withdraw credits to get money. But essentially, it's just a currency. It's not a cryptocurrency. It's not a, want to make that very clear. It's not a cryptocurrency. It's essentially just a fixed rate. Yeah, it's a fixed rate measure of compute. It's not volatile. One compute credit is always worth as much CPU time as it was yesterday, and it will be tomorrow.
If I can add some fun little color commentary, essentially what everyone's seeing here, it's a bank on top of a distributed computing platform. It's a sharing economy of compute. If someone provides as much compute to the network as they extract from it, it's free. It's completely free. So these credits they're like kilowatt hours. They're units of measurement of computational workload, and it just makes sure that everything is fair. So nobody, because this credit system, can take more from the network than they can give to it. If they want to, they have to pay. If they give to the network more than they consume, then they can get paid. And if they use as much as they consume, then it's free. So essentially, it's a unit of account and enforcement mechanism for fairness.
Doesn't that sound better than crypto? So to answer the question, that's what your keystores are. So I'm going to stop sharing for just a moment and ask Topaz, have they been sent the keystores?
No, not to this group. So we can. That's a good. We can just put the link to the folder in the chat.
Wonderful.
Do it.
I've got it open.
Okay, perfect.
So what I'm going to send you guys right now, and I'm just going to make sure you can view it, not edit it. There we go. what I'm going to send you in the stage chat here is a drive link to some Keystores. Please go in there and download default.keystore. I promise it's safe. You can delete it as soon as this is done, but download default.keystore. Once you have that, sorry, I know there's going to be quite a few instructions going at you here, but so far the steps are set up a worker, dcp.work/hackathon, enter the password DCP2021. Go to that drive link and download default.keystore. That's one of my Keystores. And now what we're going to do is in our worker here, we're going to change our address. I'll start sharing again. So we're going to take this payment address and we're going to tell our workers to work at that address. So within our worker here, we're going to hit the gear under DCP bank account. We're going to paste this value that I'm going to paste in the chat and save changes so that it appears here. There's the payment address. This just ensures that the default.keystore that you're going to be deploying jobs from also gets worked on by the same account, so that the credits that get deployed get worked on by the workers and just go in a nice big circle for our hackathon account that has some credits in it at the moment. Okay, so once some people have these hackathon workers set up, the last step is to start deploying jobs. So I'll share a job with you. We're going to do it in a Google Colab. And what's great about Colabs is that you don't have to worry about requirements or development environments, anything like that. This is essentially just a Jupyter notebook. If you're not familiar with them, that's fine. But it's just Google's flavor of Jupyter notebook that runs our code on a Google container in a server somewhere, so that we don't have to worry about it. So this is a DCP job, and you're going to see the same steps that we just talked about in tutorial in this job. These code blocks run independently. So just click the plus to start running these code blocks. So this is going to run the first one here, and you can queue them up by just pressing the plus on a few of them before it's done. I'm going to press on the first three. This is going to install Node, because this Google Colab actually technically runs a Python environment, but won't get into that. Most of our code is going to be JavaScript. All of our code is going to be JavaScript. We're going to install DCP client. This is the DCP library that lets you actually deploy jobs. And then we're going to require it and get it all initialized. Once these have run, we're going to run this one here, DCP account. And we're going to take a pause to make sure that everyone gets here. But as soon as these are finished, so there's the one finished up there, these two will be a lot shorter. Once we get to DCP account, it's going to ask us for our Keystore, the one that I just sent you, the default.keystore. Install DCP client, just requiring it. Perfect. So now it's going to ask me for my Keystore. I'm going to browse and enter my default.keystore. Okay, I'm going to take a quick pause and ask that everyone has made it here. We have a worker set up. We have the Keystore downloaded. And we have opened up this Google Colab and are running code blocks up to the DCP account part. We're going to browse for our default.keystore that we downloaded and put it into this field here, and everything is run okay. Great. Now we can do the DCP specific stuff. We are going to enter a string that we want it capitalized, so qmind should be capital. So enter a string that you want capitalized, change it up so you know that I'm not bluffing, I'm not faking it. You can enter your own string there. And then this code block here is just input set equals array dot from input string. The same thing that we saw in the slides. We're going to make an input set as an array of characters from the input string. So we run We run the capitalize input, we turn it into an array, and we have our input set. Next, we're going to get our work function ready, exact same as what we saw in the slides. Our work function takes a letter, calls progress to let the worker know that the job is still running, but it'll be a very fast job. And we return that letter capitalized. Now, we're going to make sure that our work goes to this private compute group that we've set up. So Hackathon and DCP 2021, this is the join key and the join secret for this private compute group that we have set up. This is going to make sure that this work doesn't just go out to anyone working on the DCP network, but that it goes to people only in the Hackathon group that we've set up here. So the worker that I set up and the worker that you guys set up. Now, finally, we're going to deploy our job. This is where it's a little bit more complicated than the slide, but this is really just reporting code. This is just console logging certain scheduler events to let me know if something's going wrong, but it's the same thing at heart. Let job equal compute.for, input set, work function. This just gives us a name for our job so that it appears on our workers as something that we can recognize. This initializes our compute groups into the join key and the join secret, which is Hackathon and DCP 2021, like we had earlier. This lets us know that the job is launched properly. This is console logging for results. And then we await our results, let results equals await.job exact same as the slide. And when that's done, we're just going to console log our results joined together by character. So you can see I've run this on the last string, which was hello world, but I'm going to run this again with our new string in our new compute group here. I'm going to make sure my worker's turned on Hackathon. It is perfect. And it's running. So it's going to accept this job into our scheduler. It's going to take those slices, each with one element of an input set and a work function, and begin to send them off to workers. Hopefully I won't get any of the slices. Hopefully when I launch my job here, you guys will start to get some of these slices in your workers. But if you've been keeping up, please feel free to launch this code block. You should eventually see job accepted by scheduler. That's great. And then boom, let's see. I didn't get any slices. That's awesome. Oh, I did get a few, but those might be some of your jobs. So odds are, oh yeah, definitely. I only got 7 slices and there's more than 7 characters here. So some of you guys just did some of my computing. Some of you guys just turned some of my characters into capital characters, which seems silly, but still really cool. So it's complete. QMind should be capital. Isn't that awesome? So only people within this Camp QMind Hackathon environment here received these characters. If anyone's having any issues, please let me know in the chat because it's really cool to launch this and see it happen. I'm getting 1 or 2 more slices, so at least one person is deploying work, and hopefully a bunch are just getting soaked up by other people's workers. That's awesome. If you're having any really weird errors in the Google Colab, just press runtime, factory reset runtime, and then run the code blocks again. Sometimes these Google Colabs are amazing for demonstration because they don't require you to have any node dependencies or set up your directories or anything like that. You don't even need any local code. But it's not the best with rerunning these sections over and over again. Sometimes it has issues with that. So pick your poison when it comes to development, I guess. But if you're having any terrible issues, reset that runtime. And if you're having anything confusing, please let us know in the chat. And this is deploying a job on DCP. I promised to keep it short and simple. Hopefully that did it. But what's great is that you can take this, this collab, copy some of the code out, copy those 4 steps out, the input set, the work function, the compute.for, and the await your results. And you could tear out my silly uppercase application code, and you could start sticking in some of your specific code and deploying that work on DCP. So we have a few really cool examples of this, and I think Dan is going to show one. I'm going to stop sharing here.
I was right in the middle of answering, like trying to just type away these answers to these great questions. So one of them, I'll answer right now, actually, so everyone else can hear. What happens if someone malicious on the network intercepts compute slices? For example, we're doing some very computationally expensive trajectory matching for COVID-19. One of those slices takes 7 hours to compute. So that's a big payoff when you think about it, right? Like at the end, as soon as you return a result, you'll get a nice, big, juicy chunk of compute credits. So what if you were clever, and you're all clever, you intercepted that 7-hour slice, and then you just returned 13, within a second of receiving it, instead of doing 7 hours of work and, letting your poor little Raspberry Pi chug along, right? The answer is all the other slices took around more or less 7 hours, plus or minus some performance scaling, depending on if they're really powerful or really weak machines. So if one of them comes back in 2 seconds, it gets flagged as being suspicious. And so the scheduler has a bit of like a hypervisor capability that's very nascent. We haven't really developed it yet. I mean, again, we're going to be working on this for the next 10 years. That can look at incoherence between, like malicious behavior-ish stuff. It just might happen also that you're in a region of the problem space that it's really quick to compute something. So back to my physics example, when the kernel is a very smooth function, it's very easy to calculate the area under the curve to a certain accuracy. But if it's oscillating really fast, you have to add really, really small pieces of the area because it's going between positive and negative. So you have to subdivide the interval even more. So there are regions that require more computing than others within a certain problem set. So it's normal that some slices will take an hour and others will take 10 seconds. And so figuring out if people are bullshitting answers is going to be an interesting problem in of itself to solve. Now, here's the other thing. When you're doing compute, some of the answers will sort of be within, will have the same shape. So if I'm saying, hey, I'm looking for the accuracy of some hyperparameter set, return me a percentage. Well, if you return a picture of a donkey as the result, I might also flag that result as having been manipulated and not fit with the others. So you're asking a brilliant question. How do we prevent people from returning false answers and getting paid? And though there's a whole bunch of these different steps that we're starting to implement, we're not quite there yet. Another one, the very obvious but boring one, is run compute on computers that you trust. So for example, you could go to DCL and say, well, I want my own compute group and I want to call it Josh, dcp.work/Josh. And that's the Josh compute group. And you can run around dcp.work/Josh and you will essentially have created your own compute group. And therefore you control and trust the computers. And then you can deploy workloads to your own compute network. So that's the other way. It's the boring way. It's, the computers upon which you've deployed work. So you're not worried about people tricking you because you are that person. And there's other ones. Okay, Scott, how are these computational prices compared to AWS? About 10 to 15 times less.
Great question.
Yeah. I have a whole slide dedicated to just that, but it's about 10 times less. And it's free in academic settings. Why? Because we create a compute group at the university and we just make the credits go in a circle. So the credits get kind of abstracted away, but they're there as a fairness mechanism. Any other cool questions before I jump into something slightly more advanced? But all right, okay. So
just one thing.
Yeah,
sorry. I'm just going to put my I'll put my email, but I think you might all have Topaz's email. If anyone wants that code so that they can start ripping out my application and putting in your own application, just email me or email Topaz. I'm not sure how you're supposed to be contacting us anyway. Get in touch with us and we'll make sure that you can start distributing your jobs. But Dan will have some much better examples of cool applications.
Yeah, but they tend to be harder to follow. But I can say, as a smooth transition segue here, that's exactly what I did with Connor's application. So the yelling collab you just saw, I literally took that template and I ripped out like the string and I put in some, well, actually I can't take credit here. I didn't do this at all. Give credit where credit is due. Chris McIntyre, one of our team members, also studied at Queen's and is now part of the AI task force. He ripped out the code from Connor's template and put in the MNIST hello world example, right, of machine learning. So we're going to see some pretty familiar stuff if anyone has touched MNIST, and I think everyone has because it's pretty standard tutorial. We're doing MNIST hyperparameter tuning DCP style. So sharing screen and going into it. Et voila. So this collab, which I think we can also share, well, we definitely should and will share. We just give a background of what the MNIST example is. So that's essentially pretty standard. We're giving it a database of handwritten numbers, and the goal is we want to select optimum hyperparameters upon which to train our neural network models to get really good at being able to have a machine model recognize handwritten numbers so that it doesn't have to be a human. And so the stack here is Colab, obviously, with a Node backend. We're going to use DCP in there, and of course TensorFlow, the JavaScript version of it. And the
Dan, if I could interrupt you for just a minute, we have a really great question in the chat about how you deal with supply and demand shock.
I have a whole diagram for that. You know what? And I'm going to show it. So let's talk about that. I you know what? I much rather any day to just follow what people want to talk about. So this is called network diagram effect. All right. So let's start. I love these tangents. If you hopefully you see my screen, this is Uber before they became Uber. They're like, okay, well, if we have a lot of drivers, that means there's going to be a lot of geographic coverage. And if there's a lot of geographic coverage, then there'll be faster pickups. And if there's faster pickups, the clients will be happier and more people will like Uber, and therefore you get more demand. If there's more demand, then more people want to sign up to be drivers, and the virtuous cycle goes in circles. But what you see here is that there's actually two circles. There are two circles because more geographic coverage doesn't just mean faster pickups. It means less driver downtime. So if you were a driver and you showed up and you never get called or hailed for a ride, you'd be like, well, that sucks. But instead, because there's more geographic coverage and more customers, then you as the driver are you're going from one ride to the next making money. But if there's less driver downtime, then you're happy to do it for a lower price because, if you're only going to get one ride in a day, it better be worth your while to, buckle in and get out there and do some drives. But if there's less driver downtime and there's more demand, you can lower prices and compete with everyone else, blah, blah, blah. And lower prices also leads to more demand. And this just goes in a nice fat circle and made Uber worth $10 billion. So here's DCP, or at least what we're hopefully, we're not trying to take something and make it more complicated. We actually accurately tried to describe how we think this is going to play out. So again, same thing. If there's more clients and there's less worker downtime, again, if you click the start button and no tasks show up in your computer and you're like, well, that sucks, you'd leave. But if there is enough work and there's less worker downtime, well, that's going to lead to higher job prices. Right? More higher job prices is going to attract more workers who will compete. The more supply there is, the lower the job prices. So we just went in a circle there. Lower job prices means more clients. And I'm going to talk about the demand shocks in a second. But higher job prices does something else. What we didn't tell you about today, which is firmly part of our essential critical roadmap, is we're going to build in a royalty system into DCP, where people building apps that then get used by other people, they get to collect a piece of the credits that get consumed by people using their apps or their libraries. Think about that. If you build something really freaking useful, like a really efficient numerical integration routine library, and half the world starts using it for their math apps, you can scrape 2-3% or whatever within reason. Or maybe let's say you can scrape 10%, right? Until someone else comes along and builds a better math library, and then they compete with you and they say they're only going to take 8. So we're incentivizing this race to the bottom, but for building a rich ecosystem of applications and libraries that can be done through a marketplace. If there's more applications and libraries and functions and this and that to choose from, it was not all clients are user developers. Some of them are just users. Like they just want to detect and count cars, right? They don't care to build the actual car counting application, but they'll just pull one from the market that someone else would have built. But if there's more apps, then there's lower job prices, and because now even the developers are competing amongst themselves to build apps and libraries. And of course, if there's more apps and there's more of a richness to choose from, then of course you get more clients, and this whole thing goes in a virtuous cycle upwards. The demand shocks come as follows. If all of a sudden there are suddenly, and all these loops, right? The more they go in a circle, the stronger they become, and you create this positive network effect. But you can create negative network effects where all of a sudden, if there's less DCP workers, all right, so now there's a lot of demand all of a sudden, but there's not enough workers to keep up, right? Let's say there's 10,000 jobs, but only one computer to compute them. well, the demand side is gonna say, well, this frigging sucks. This is not a supercomputer at all. This is just one computer running my job remotely, and then they're gonna leave. So less workers and would cause this thing to start going backwards. And the same is true on the other side. If there are too many workers and not enough demand, they're going to show up, they're going to click the start button, and there's going to be no work coming in through, and they're going to say, well, this sucks. So the two ways you can mitigate the demand shocks: if there's too much demand, that's an easy one, because eventually if there's too much demand, the prices go high enough. Well, eventually they're going to match EC2 spot instances or commercial cloud. We hope they don't, because that would suck. That would defeat the purpose of creating a cloud in the first place. But if they did, whatever, we'll just automatically have scripts deploying DCP workers to EC2 spot instances that will soak up the excess demand until such a time that high price will set up all kinds of alarm bells around the world, and people will be like, holy shit, it's profitable to run DCP workers, and then they'll bring their workers online to go soak up that demand, and that will bring prices back down again. And then on the other side, and so that's easy. So too much demand, not enough workers, that is brain dead easy to deal with. The really hard one is what if you have too much supply, not enough demand. And guess what? That's where compute networks and platform curators and launchers, that's where the real war, that's where the real value add comes in. And so what we're doing that's different from everyone else. Everyone else is trying to do cryptocurrency bullshit, and that really incentivizes just the workers. So it's like a double whammy for them. What you need to do to have a successful demand-driven computing network is to create something freaking useful and easy to use that actually adds value with no bullshit. So what we're focusing is make an API that is 5 lines long, super easy to use, and actually adds to a developer's experience. Make it free for academia. So we put our money where our mouth is in terms of trying to have an impact. So make this free for academia worldwide. Get every researcher and student and person that needs to do compute, equip them, perpetually for free in their university networks to be able to do work. And then on the outside, for everyone else, well, make sure that it's not bullshit. Make sure that this thing is cheaper than cloud. Make sure that it is satisfying and useful to use, and empowers people. So I really went off on a tangent here talking about, and then we could pick all of these up. Look at this, boom, 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 boom. Like we could describe literally every single segment in this, but I won't do that now. I'm happy to get in touch with folks to do a deeper dive if ever you want. Does that answer the demand shock questions? I hope so. I assume so. Okay, so now I'll go back into, I'll reshare my screen and go back into the hyperparameter tuning example. Okay, so Connor was showing this almost identical collab. The only thing that changed is the title and some of the code within those blocks. And we sort of skipped over the interview here, the overview, but this is kind of cool. This explains like the DCP library sort of and how to use it in like a single screenshot. So the steps here are exactly what Connor walked us through. Set up your compute supply, so you can either join the public network, earn credits, and then launch your work to the public network and spend credits. Or if you have a join key and join secret like Hackathon and DCP 2021, you can do it within a private compute network, either or. You set up your DCP client package. You declare your input set, which is an arbitrary enumerable data set, MP3 files, hyperparameters to test, and that's what we're going to do today, images, Blender project file, whatever. You define your work function, which is an arbitrary work function that you have written, and you can do cool things like require a TensorFlow.js or other packages. Like for me, I wrote a bunch of physics code that I want to compute. And in this case, we're going to use neural networks, inference models that we're going to distribute. You express your job by applying compute.for syntax, and all it does is automatically map the work function to every element of the input set, and optionally specify the compute group, which was the stuff we talked about up here, and you just await your results. Voila. So same thing. You've already seen this. So we're deploying Node.js, or we're configuring it. We're configuring the DCP environment. Here, there's something called Bifrost. I don't want to go too deep into this, but this is a magical library that allows Python to JavaScript or Python to Node object cross functionality. And we're going to get into that later. Not now, that's a little bit more advanced, but the ultimate goal is let people write Python, but also benefit from the distributed compute of DCP magically without needing to worry about the JavaScript in the first place. That's more advanced stuff. But anyway, DCP API key, same thing. I'm giving him my Keystore. Input set, these are the hyperparameters or the tuning parameters we want to test. So down here, this is it. So if you've seen, this is not our code. This is literally from the MNIST tutorial. We're setting the hyperparameters, or we're producing them, selecting them at random. And you can see here's all the sets. Each line here is a set of hyperparameters that we want to evaluate for its accuracy. The work function, this is our neural network model that's going to train on each of these individual hyperparameter sets and return essentially a loss function and a fit, an accuracy, and we're going to pick the best one. So this too is, you can see we're requiring TensorFlow and all that other stuff. And none of this is our code. We just took it from the existing tutorials. And yeah, so this work function, all it does is it takes the parameters, the model parameters as an input, and it's going to return the loss and accuracy. And this is exactly identical in a sense, or at least functionally, to what Connor showed, where the input is a letter and the output is an uppercase. So that's it. Work function takes its input parameters, outputs accuracy, and now we're at the compute.for. This part is easy. One line of code. Compute.for, take the input set, which are all those, that iterable array of parameter sets. The work function is the neural network that we're going to map onto each input parameter set, and then we have as an argument the training size. That's all the there's one more thing obviously that's going along with for the ride here. It's all the handwritten images. That's essentially the training set. So then the rest here, this is just some quality of life stuff. We're giving this job a public name, so whenever people are doing compute, they can see this show up. We're requiring the TensorFlow.js and the sharded MNIST data set. And that's it. The rest of this is just eventing that we're also getting. So this is going to tell us that the job's accepted and all this other stuff. I mean, normally you don't need this. You just put it in so that you know that, you didn't just deploy a job into the ether. And then whenever you get slices back, it'll console.log. So that's it. So that's setting up the job handle. And as you recall, the last step is just call execute. So here, optionally, we can send it to a compute group, and here it is. So await, let results at await job exec, and if I let that rip, this is what it would look like. So here's the ready state changes I was talking about. The job is deployed. It gives us a unique identifier for the job that was that went out. Here, I mean, this job's complete. You can see that it starts off as 40 slices are sent off to DCP. And initially, of course, nothing has been done. And then you can see as results come back, boom, 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 boom. The job will just rip through all of these in parallel until you get all slices computed and you get your best results. And instead of doing this in series, you can do this just in parallel over as many computers as you can hijack. Or by hijack, I mean recruit into your compute network. So that's it. That's a much more complicated example, but it's using a standard, the standard MNIST tutorial, and we've just overlaid that to our existing template for environment, DCP client, input set, work function, compute.for, execute. Are there any questions?
Thank you so much, Dan. I think unfortunately we ran out of time for further questions. No, that's all good. And I see, Max is coming in to tell us our time is up. But I did want to say one final thing is that just so everybody knows, I will share all this information, all these links with Max, so we can include that in the package, as well as this is only one of the first sessions that we will do this year with QMind, and really looking forward to showing you more demos and examples, and hopefully supporting some of your projects. So we'll send all of this and know that this is just the start. So thank you so much, and thank you, Max, for being generous with the schedule with us. Thank you.
Yeah, thank you.